let's have a look at a couple of the problems from the quiz for week 2. Number 7 seemed to cause some trouble for people. I think maybe it was just the problem was figuring out what exactly to enter here. So based on questions I got on homework, or questions I got in email and in office hours, it seemed like not everyone really knew what this is asking for. So this first line says that x should be, let's see, so right, here's our augmented column. So x should be minus 3 minus, so x, y, z, w, u. So minus 3 minus 3z plus 3u. And then the second row says that y should be 3 plus 2z plus 2u. And then the third row says that w should be 1 plus 5u. Okay. Now if we write this vector style, right, what this is really asking for is, so we've written the solution, we've parameterized all the solutions to the system, but what we're really asking for down here is the vector version of the parameterized solution. So we need to express this in terms of vectors. So our solution looks like x, y, z, w, u is, so x is minus 3 minus 3z plus 3u. Y is 3 plus 2z plus 2u. Z, well, z is a free parameter, so z is just z. W is 1 plus 5u. And u is a free parameter, so u is just u. Okay, now we need to pull this apart to look like what the question is asking for. So what we can do is split this big vector up here and here. And that gives us the first vector, minus 3, 3, 0, 1, 0, plus, and then our second vector is minus 3z plus 2z, z, 0, 0, plus, and then the last vector with all the u's is 3u, 2u, 0, 5u, u. And now these last two vectors, every entry has a z for the second one, or a u for the third one. So we can pull those variables out as scalars. So minus 3, 3, 0, 1, 0, plus, now we can pull out that z, z times minus 3, 2, 1, 0, 0. And then we can pull the u out. So plus u times 3, 2, 0, 5, 1. Okay, and these are the vectors that we need to enter up in the answer boxes up here. The other problem that I wanted to look at from the quiz was this balancing a chemical equation. So, you know, if you've taken a chemistry class, this equation is actually pretty straightforward to balance because carbon only shows up in one place in the reactants and one place in the products. So it's actually pretty straightforward to balance, sort of chemistry class style. But if we want to write this in terms of a linear system and sort of do it linear algebra style, we would do this. So here is our reaction equation with the coefficients in front. Now looking at carbon atoms, for reactants we have 7A, and for products we have, I'm going to remember when we do this, the products end up, once you move everything to one side, the products always end up with negatives. So I'll jump to that form straight away. So for products, for carbon, we only have minus, because it's a product, little c times 1. Yeah. Okay, so equals 0. Right? This difference has to be equal to 0 because we should have the same number of carbon atoms at the beginning and at the end, because this is a chemical reaction, not a nuclear reaction. Okay, now looking at hydrogen. For reactants, we have 6A. And for products, hydrogen only shows up right here. So minus 2D equals 0. And then for oxygen, we have 2A and then plus 2B. And for products, we have minus 2C and minus D equals 0. Okay, so this is a homogeneous system. So now we can write down the system. So here's our A column, B column, C column, and a D column. So 7, 0, minus 1, 0. Now the hydrogen row, so 6, 0, 0, minus 2. And then for oxygen, 2, 2, minus 2, minus 1. Okay. Now, to solve this, we need to row reduce this. So I'm going to plug this into a row reducer because I don't want to do it myself. You know how much fun doing row reduction is for the 100th time. So I'm going to ask Sage to do it, and I'll be right back. Okay, so when I ask for reduced row echelon form, I get 1, 1, 1, and minus a third, minus 5 halves, and minus 7 thirds. Okay, so this means that, so remember this is a homogeneous system, so this is the A column, the B column, the C column, and the D column. So this means that our solutions look like, so first of all, D is a free parameter, right? And C has to be 7 thirds D. B has to be 5 halves D. And A has to be 1/3 D. Right? Or if we wanted to pull that scalar out, we could write 1/3, 5 halves, 7 thirds, and 1. Okay. Now, since this is representing numbers of molecules in a chemical reaction, the number of each molecule has to be an integer. So we need to choose a solution that is as small as possible, but also all integers. So we just need to plug in a value for D that gets rid of all of these denominators here. So we need to for D, we need to choose the least common denominator of these fractions, but that's going to be 6. So we need to plug in 6 for D. And when we do that, we get, so 1/3 times 6 is 2, 5 halves times 6 is 15, 7 thirds times 6 is 14, and then 1 times 6 is 6. So this is A, B, C, and D. And that tells us the coefficients for the molecules in our chemical reaction.